Previously, we have looked at solutions to the system of differential equations y prime equals a times y. Now, solutions looked like y equals e to the lambda t times v, where lambda was an eigenvalue of a and v was an eigenvector of a. We looked at some specific cases for 2 by 2 matrices A. We looked at lambda 1 and lambda 2 being real eigenvalues that are distinct. That gave us two solutions of this form, y equals e to the lambda tv. We also looked at cases where lambda was of the form a plus or minus b times I. So we had two complex roots to our characteristic polynomial. And in those cases, we had to look at what the complex exponential looked like. And we turned it into cosines and sines using Euler's identity. Now I'd like to look at the case where a has a repeated root of the characteristic polynomial, so that there's only one eigenvalue lambda. Now, there are two different cases that we can look at when lambda is the only eigenvalue of our 2 by 2 matrix. The first case is a diagonal system. So we have ddt of the vector xy is equal to lambda 0, 0 lambda times the vector xy. And what we really have here, if we write out each equation individually, is that x prime equals lambda times x and y prime is equal to lambda times y. And both of those equations are decoupled, meaning that x does not depend on y and y does not depend on x. So we can actually just solve these two equations individually. X of t is just a constant, maybe we'll call that constant c1, e to the lambda t, and y of t is another constant, we'll call it c2, e to the lambda t. And so what we really have is not a system of differential equations, but just two unrelated differential equations. We could write the solution to this system in vector form. We can think about it as c1 e to the lambda t times 1, 0, so that we just have the solution of the x equation, plus c2 e to the lambda t times the vector 0, 1, so we just have the solution to the y equation. But this is not really the interesting case that we want to look at. We instead should look at a non-diagonal system where y prime equals a times y, but it only has one eigenvalue lambda and one eigenvector v. In that case, we can write down one solution. It looks like e to the lambda t times v, as we stated before. We'll call that solution y1. But we know we need to have a second solution that's linearly independent. And the question is, how do we find another linearly independent solution? Now, we can go back to what we learned from looking at second-order differential equations. When we had a repeated root of the characteristic polynomial, we just took the first solution and then multiplied it by t. So we could, in fact, if we wanted to, let our second solution be y2 of t, and we could think about it as being e to the lambda t times tv. But it turns out that's not actually going to be sufficient. Instead, we're going to multiply that by w, another vector, plus t times v, where v is the eigenvector. Now we want to substitute this back into our system of differential equations to see that it will indeed work out. So let's take the derivative. I'm going to take the derivative using the product rule. That gives me lambda e to the lambda t times w plus t times v plus e to the lambda t times the derivative of w plus tv, which is just v. I'm just going to rearrange these terms a little bit. I'm going to have lambda e to the lambda t times w plus e to the lambda t times v, bringing in this term. And then finally, lambda e to the lambda t times tv. Well, y2 prime is supposed to be equal to a times y, so we should see what that is. That is going to be a times e to the lambda t w plus t times v. Well, that is e to the lambda t because that's just a scalar. And that's going to be multiplied by a times w plus tv. And then I'm going to distribute the a. So I'm going to get e to the lambda t times aw plus e to the lambda t times t a v. But in this case, we should note that a times v is in fact lambda times v, because v is an eigenvector. And so when I set y2 prime equal to a times y2, then this term, e to the lambda t lambda v, appears in both y2 prime and a times y, so they cancel. And so now, comparing what I have left, here I'm going to assume that e to the lambda t is greater than 0, because lambda in this case with a repeated root is going to be real, and so exponentials are always positive. What I have left in comparing is that a times w equals w plus t times v. Sorry. A times w is equal to w plus t times v. There it is. Oh. A times w is equal to lambda w plus v. Much better. Okay. So comparing what is left, we have a times w is equal to lambda w plus v. Another way that we can write that is we can look at that as being a minus lambda I times w. So here we're going to bring this over to the other side. Equals v. And so what we have here is something that looks similar to the problem that we had to solve when we were finding eigenvectors. When we were finding eigenvectors, we had to solve a minus lambda I times v equals 0. But instead, now we have a minus lambda I times w equals our eigenvector v. Well, in solving that, so if w solves the problem a minus lambda I w equals v, we say that w is called a generalized eigenvector. And it actually satisfies a property. So it turns out that if you look at a minus lambda I squared times w, that in fact is a minus lambda I times a minus lambda I times w. But a minus lambda I times w is actually equal to v. And a minus lambda I times v, because it's an eigenvector, is equal to 0. So the generalized eigenvector actually solves a minus lambda I squared times w equal to 0. So essentially, if we have to solve a problem with a repeated eigenvalue, so you would have to find the repeated eigenvalue, and the corresponding eigenvector b. Then you would solve a minus lambda I times w is equal to v to find w. Our generalized eigenvector. So previously we had solved a minus lambda I times v is equal to 0. And then finally, our general solution would be y of t equals c1 e to the lambda t v plus c2 e to the lambda t times, looking at the form of our second solution, it would be w plus t times v. And that gives you the process for finding the solution to one of these systems of differential equations where the matrix has a repeated eigenvalue lambda.